Justin Miller, Exxon College Physics here. What are we doing today, you may ask? Physics, of course. But what kind of physics? We're gonna go ahead and start looking at more stuff regarding waves. And what we wanna focus on now is wave interference. So, if we have more than one wave occupying the same space, whether it be traveling across the string, or a wave in air, or even light waves, we can have what is known as interference. The waves themselves overlap spatially, and they're said to interfere with one another. What does that mean? Do they mess each other up? No, not necessarily. What ultimately happens is that they add together. They add together because there can only be one overall displacement of an air molecule or of a string element at a given location at a given time. We can't have an element on a string that has two different waves in it be up here and down here simultaneously, right? So there can be only one overall displacement of any one particle or any one position of an overall wave that's due to multiple waves overlapping. So what do we have with this? Superposition. So we can just start with this. When two or more waves occupy the same space at a given time, they are said to interfere with one another. Basically, they add together and produce, let's say, a new displacement. New displacements of the material through which they travel. That's not the case for light waves. There is no necessary material, but material basically, they add together and produce new displacements of the material through which they travel by the rules of superposition. The rules of superposition are basically, well, just that. They superimpose themselves on one another. They add together at every point in space that they overlap. Their displacements add together at every point in space that they overlap at any given moment in time and produce the overall displacement. So consider two waves, y1 of x and t and y2 of x and t. These two waves overlap spatially. They will produce a new wave given by sigma y of x and t is equal to y sub 1 of x and t plus y sub 2 of x and t. That's it. We just add up the individual waves together, add up their displacements at the given positions at the given times, and we get ourselves the new wave. That's superposition right there. So, what do we want to do with this? I'm going to take a couple little examples and sort of look at aspects of superposition and some novel things that fall out of superposition. So first off, let's look at two traveling waves that are going in the same direction that have the same frequency and travel at the same speed, but are maybe out of phase with one another. Now consider that y1 of x and t is equal to a times the sine of kx minus omega t, and y2 of x and t is equal to a times the sine of kx minus omega t plus some phase constant here. So we're going to say this: y1 and y2 have the same frequency and same wave speed. And given that, thus they have the same wavelength too. They're identical waves, except y2 is out of phase relative to y1 by the angle phi. And we put minus here, so they're both traveling to the right. So they're both traveling in the same direction. So the plus x direction or positive I add, whatever you want. All right, so we've got these two waves. They're out of phase, possibly out of phase by some angle theta, phi, which could be 0, I guess, so they're not out of phase. But what do we want to do? We want to look at the new wave. The wave that results from y1 and y2 interfering is, we'll begin, rules of superposition. Sigma y of x and t is equal to y1 of x and t plus y2 of x and t. What does that equal? Well, let's go ahead and check this out. We've got this is going to be equal to a times the sine of kx minus omega t. There we go. There's y1 plus a times the sine of kx minus omega t plus phi. Alrighty, what do we have with this? Well, we've got a common factor of a. That's great. We can factor out that a and have the sine of kx minus omega t plus the sine of kx minus omega t plus phi multiplied by the amplitude a. That's a fantastic. So what we have here is the ability to start to utilize a trig identity, or a trig identity. So what can we do with this? Well, we can note that the sine of A plus the sine of B, we can write a little trig ID, trig, I just call it a trig relation here. That can be written as 2 times the cosine of A minus B divided by 2 times the sine of A plus B divided by 2. That comes in handy sometimes. It's going to come in handy here. Why do you say? Well, let's go ahead and see what happens when we say that the sine of A plus the sine of B is equal to this. Well, what is A and what is B? Well, in our case, A is going to be kx minus omega t. And B is going to be equal to kx minus omega t plus phi. phi. So I don't need to close that there. Go like that. Pinky in the way. All right, so what happens with all of this? Well, this is going to get a little big here. And then it'll reduce down, so let me just get rid of this here. Make a little room. All right. What happens? Well, we just go ahead and do this, right? So we've got sigma y of x and t is going to be equal to, we're going to have that 2 times that stuff, and we're also going to have a factor of a. So I'm going to write it out like this. 2a, is that common factor a? Then we've got the cosine. The cosine of this quantity, we have a minus b, so we've got kx minus omega t. There's a, then minus b is minus kx plus omega t minus phi. So I distributed the negative sign through b there. And then this is all divided by 2. And then we've got ourselves the sine of a plus b over 2. Kx minus omega t plus kx minus omega t plus phi. Divided by a 2. All right, so does anything fancy happen with any of this? And if we say, yeah, I see some fanciness, what do we see in here? Well, here I've got a minus omega t, plus omega t, and I've got a kx and a minus kx. Huh, looks like all that stuff's gonna cancel except for this. We've got minus phi over 2. All right, so let's write this. We've got, this is going to be equal to 2a times the cosine of negative phi over 2, but the cosine of a negative angle is the same as the cosine of the positive, right? Cosine's an even function. So I'm just going to get rid of that negative sign because it's not necessary. It doesn't change anything. And I'm just going to simplify things and call this positive phi over 2. Again, cosine's an even function. So we've got that portion. Then what do we have over here? Any fancy stuff here? We've got a minus omega t and a minus omega t, so there's minus 2 omega t, and we've got a kx and another kx. So there's 2 kx's. So we've got 2 kx minus 2 omega t plus phi, and then that's all divided by 2. What's that going to be? Well, we're going to have this. It's multiplied by the sine of 2kx over 2 minus 2 omega t over 2 plus phi over 2. So some of those 2's cancel out, right? And we got ourselves kx minus omega t plus phi divided by 2. All right, so what does this mean? What does this mean? Well, this is what we get out of these 2 waves that are traveling in the same direction, that are identical waves, interfering with one another, that are out of phase with one another by some angle phi. So let's get this first. What happens if phi is equal to 0? If phi is equal to 0, what does that mean? y1 and y2 are in phase, completely in phase. In terms of somewhat a little drawing here, what would we have? Well, we would have ourselves y1, at some moment in time, or x and t, whatever you want to do, but this is what it looks like. And then we'd have a y2, and those are supposed to match up, which I did a really not good job. First one started out okay, this one, and then I went awry over here. So this should pass there, go up, go down, go up, go down. So identical, right? There's y1 and y2. What happens when we add those together? Really, if we're doing this graphically, it's point by point. This point here, the displacement here, adds with the displacement there, which is 0. this displacement here adds with this displacement here, which is that plus that, which makes it like that. This displacement here adds with this displacement here, which is that plus that, which is then 2 times that, right? So if I were to draw this out, you would have amplitude doubles. This is going to get a little messy. Okay, let me not do it there because that just isn't going to work. This will be easier for me. Anyway, here is sigma y. We've got, there's A, there's 2A. There's minus A, there's minus 2A, and we would have, we have this new wave. Now this new wave has the same frequency, omega, has the same wavelength, well, that's angular frequency, the same wavelength, 2 pi divided by k, as the individual 2 waves because they were identical, and travels at the same speed. What's different between this one and these 2 individuals? Well, this one has twice the amplitude. This again is if they're completely in phase. Phi is equal to 0 degrees. In phase, they add together, and we call this constructive interference. They add constructively to make something bigger than the individual waves themselves. And this is complete constructive interference. We've made something as big as possible. This is the biggest outcome that we can have in adding those 2 waves together when they're in phase. Because what is this reduced to if phi is equal to 0? This is right here. Well, if phi is equal to 0, we've got the cosine of 0 is equal to 1, and we've got this right here. So phi is equal to 0, that term goes away, and we're left with this. Sigma y is equal to 2a times the sine of kx minus omega t. Same frequency, same wavelength, same wave speed. What's different? Amplitude is doubled. It's the only difference. Constructive interference. That's what we call that. Constructive interference. Just add together to make something bigger. Okay, well that's if phi is equal to 0 degrees. 2 identical waves in phase. What if we look at the other end of the spectrum and said, you know what? These waves are out of phase by half of the cycle. What is half of the cycle? Well, half of the cycle would be equivalent spatially to half of a wavelength, or half of the period temporally. Ultimately, it's a phase shift of pi radians. So now, look at phi being equal to pi. Y1 and Y2. Out of phase in terms of a cycle by half of a cycle. So what ends up happening with this? Well, in terms of the expression, we've got sigma y would be equal to 2a times the cosine of, now we've got pi over 2. Cosine of pi over 2? Oh, that's right, that's 0. Ooh, so that term's 0 there. And then we've got the sine of kx minus omega t plus pi over 2. Yes, pi over 2. But it doesn't matter. This term's equal to 0. So this whole thing is equal to 0. It says that the displacement at any position at any time is equal to 0. What the heck does that mean? Well, let's look. So now we would have our y1, we could say is like this, just as before. But y2 relative to y1 has a different phase relation. out of phase by 180 degrees, pi radians, or half a cycle. So how do you get this? Well, you think about this in terms of cycles, right? There's one complete cycle. That is 2 pi radians. So what's half of that? Right there, there's pi radians. So if we took this portion out and shifted this whole thing over, that would be where we start at relative to the other one. That's a 180 degree phase shift. So instead of going up then down, we're going down then up. So we go like this. That's super bad, huh? Yeah, that was pretty bad. Let me try that one more time. Make some little marks for myself. So we're going down and up, up, down, down. I'm totally cheating, but it's hard for me to match these up. Something I just always struggle with. Now, it's connecting the dots is sometimes even harder than drawing them. Something like that. So what happens? Well, when we think about adding these two together, still right here, 0, 0, but when we start getting anywhere else, that adds with that. Well, this is below the x-axis or t-axis, pick one. This is above. This plus this is 0, and that happens everywhere. Everywhere that these two add, this is above, this is below. We have 0. They collapse on one another. This is destructive interference. We get the waves cancel each other out. So instead of adding together and producing something bigger here, they add together and produce, well, in this case, nothing. Complete destructive interference. All right, so those are some nifty things that can happen, and then there's the whole in between. What happens in between? Well, we'll have to take a little bit of a look at that. Yeah, we'll look at that. So, what do we got? We got this expression, so let's just straight up look at that and see what the in-between's all about. Erase this so I don't need to even write that out again. So, what do we get? We get a wave that has the same angular frequency, has the same wavelength, and thus has the same wave speed. However, the amplitude of that wave is governed by this first portion right here. Over here. That is the resultant amplitude. The resultant amplitude depends on the phase angle. Sinusoidal nature preserved. The only difference is that it could be offset phase-wise, depending on what phi actually is. Of course, for phi equals 0, or phi equals pi, there is no overall offset because either it's the same or it's 0 overall, the wave. But for phi in between 0 and pi, we do have that the overall wave is phase shifted relative to y1 by an angle phi over 2. Same wave characteristics. The resultant wave shifted by an angle phi over 2 relative to y1. There we go. That's it. So guess we can draw one more thing, attempt 2. So we could have something like this, right? I'll draw them over here. We could have one wave that looks like this. We've got ourselves a Y1 there. We have another one, Y2, that looks like, just do it a little bit. Starting at the same spot here. There. Y2, that looks like, just do it, sine where it's shifted by 90 degrees. Something like this, where this one's not quite starting as a sine or cosine. It's somewhere in between phase shifted. Well, what happens then? Well, we add up this plus this for where the one wave, the resultant wave starts, and then kind of go from there. So where would that be? It would be starting like this one, but we would have that it's actually added together differently. And this isn't going to be perfect, but we kind of get the idea across here. The resultant wave, sigma y, which is something like starting off here and then increasing a whole bunch. The biggest increase would be somewhere in between those both. Something like this, somewhere around this, where the phase shift of this one overall relative to the first one is half the phase shift of this one. The phase shift of this one, it wasn't phase shift that much, but half of it. So, there we go. Same wave, same wavelength. Not showing too good there wavelength-wise. Oof, that is not good. Still need about this much spacing in between the peaks. Maybe something like that. So wavelength's about the same. It should be exactly the same. It's just shifted over phase-wise. All right, we'll leave it at that. Drawing these things out is best left to a computerized system. But anyways, that's what we got. It's pretty cool to see. Get an overall new amplitude, same wave, just different starting spot. We add two together that have the same wavelength, same amplitude, and same wave speed. All right, until next, we'll get some more interference. Take care.